Hello, everyone, and welcome to VSA Online. So this is my pleasure to start this session and welcome Chatterjee Abhijit from Georgia Institute of Technology and Mohamed Mejri from the same university. So they will give a talk on reasoning using hyperdimensional computing, which is really exciting. So without any further delay, the floor is yours.
Thank you. Okay, so my plan is to give you a high-level overview of the problem, and then hand the baton over to my student Mohammed, who will talk about specific implementation details. So our system is called Resolve, and the problem is reasoning in hyperdimensional spaces with relational and object-level features using vector symbolic processing. So the slide is controlled by Mohammed. And I'll do the introduction and then he'll take over. So Mohammed, can you get me the next slide? Hello.
Let's see if yeah, I see him online. Mohammed, hello? Yes, okay.
Okay, so I think yeah. So before we jump into details, just some high-level vision of the problem that we're trying to solve. And what we want to do is we want to do some, what we call reasoning tasks and see if we can reason using vector symbolic architectures. So the specific thing is that, the specific problems that we're looking at deal with abstract reasoning tasks that link input data to output data through a hidden rule. And what I mean by that is going to become clear as I give you some examples. So basically, there is input data and there's output data, and there's some structural information in the input data that you need to abstract by just studying the data. Effectively, the structure defines specific problems that you're trying to solve and reason about these problems and come out with an answer. The answer could be a yes, no kind of an answer, like a binary answer, or it could be maybe predicting a new object or uh, uh, basically some logical extension of what I'm trying to reason about. And the goal is to extract the structure automatically from data. So we will not tell you what the mathematical rules are of this particular structure that I'm talking about, and you have to learn that from the data itself. One key goal is to learn from minimal amounts of data. So can we minimize the amount of training data that you need for the system to figure things out? And the second goal is to minimize compute complexity. So we really don't want to do massive amounts of computation. See if there are some hypervector encoding mechanisms that can help you reduce the number of arithmetic computations that you need. And a simple example is sort of given in the bottom of the slide. So, so if you're checking for palindromes, so for example, Bob and Eve are palindromes. And let's say I give you three letters or names and ask you, is this a palindrome or not? But the rule for a palindrome is not known to the AI system. So the learner does not know that I'm looking for a palindrome. So for example, Joe is not a palindrome. And a palindrome is a word that reads the same forward and backward, right? So basically, if I give the system enough examples of palindromes, then can it recognize palindromes from arbitrary data? And the goal is to be able to do this with while minimizing the amount of training data that I need. Next slide. So abstract reasoning, you deal with various levels of information. There's object level information. So are you dealing with images? The image itself is an object. It could be a triangle, a square, or maybe a cube. That's object level information. There's also relational level information. So you need these different types of information to be able to reason about the problem. So you need to know about the object. You need to have relational information, meaning that basically in the palindrome Bob, the relationship between the first B, the middle O, and the last B, and so on. So how are different uh, sequences of objects related to each other? So that's relational level information. And of course, positional information deals with where that object occurs in that sequence. So we're going to be talking about sequences of objects and reasoning with sequences of objects. And where a particular object occurs in the sequence is important. So three types of information: object level features, relational information, and position level information. Now, so this slide gives a very high level overview of the kind of problems that we're trying to solve. And it shows something, a bunch of pictorial examples taken from Jonathan Cohen's paper. Jonathan Cohen is a professor at Princeton. And of course, Raven's matrices are very well known in psychology. They're generally used as IQ tests for children. And these are some examples. So the first picture, A, asks a simple question: are these two things, the triangle and the square, are they two different objects, or are they the same object? So this might seem like a very simple problem, but deep neural networks have trouble solving even a simple question like this. One can, for example, change the orientation of an object or present it in a different perspective or with different geometry, and the problem becomes difficult. But this is the simplest version of the problem. Problem number B, as you see, you're given sequences. So for example, you're given a sequence of two triangles, and then you're given two options at the bottom, 1 and 2, and you have to figure out which one fits what is the most reasonable from what the algorithm has seen earlier, which is two triangles. So in this case, the two pentagons match should be the right answer, because basically what we're looking for are two shapes that are identical. The problem number C is a little harder. It's called the distribution of 3. So you can see that the top row has a circle, a square, and a triangle. And then you're given a triangle, a circle, and a blank, and you're supposed to fill in the blank. So how do you fill in the blank? The blank has to be basically the missing object from a circle, a square, and a triangle. So it has to be the square. And then there are various things like, for example, and of course, you see these rules you can make these rules very, very complicated. And these problems, these are called Raven's matrices. And these are essentially used to check for intelligence. These are basically intelligence tests. And the last problem you can figure out essentially this blank box has to be a circle, since in the top picture the two pentagons are the first and the last objects. Okay, so any questions so far? I'm good to go.
Yes.
Okay, next slide. Okay, so the broad thing right now, everyone's looking at transformers. Transformers are the be-all and end-all of all AI. The big companies, they've invested so much money into transformers, everything, all the chatbots, everything, they're running off of transformers. So these are great at extracting features and handling sequences through attention. But transformers have a problem. The key problem with the transformer is that what transformers do is they create query, key, and value vectors, which are linear transformations of object embeddings. And then you compute an attention score, which essentially mixes the value vectors using some confidence metrics, essentially through a softmax operation, and then it generates a vector which is then passed on to future layers for processing. The problem with this is that object level features and relational, there's a lot of mixing that happens between object level features and relational information, and relational information, which makes basically the kind of reasoning tasks that we want to do difficult. So what the broad understanding in the AI literature is that you need some kind of symbolic processing, and where symbols represent objects, and one can essentially quantify relations between symbols and somehow delink object level features from relations between objects to be able to reason about various problems. And that's where hyperdimensional computing plays a big role. Essentially, there's something called the superposition catastrophe, which happens with transformers, which we want to avoid. The whole problem is one where object level features and relational information become entangled because of the mixing that I was talking about. Next slide. Okay, so the first work in this area was very interesting. It came from Princeton, where they invented something called the embedded symbol binding network, and there's been some follow-up work called the abstractor. I'll talk a little bit about the ESBN, and then Mohamed will talk about the abstractor. And the ESBN was one of the first architectures which basically proposed a mechanism for disentangling relational from object level information. Now, the initial architectures, including the abstractor, go to great lengths to do this, to enable this separation. But what we've discovered is if you completely separate these two, then that's not good either. It creates problems for certain classes of problems where you need both. You need some level of mixing between object level information and relational information to solve certain classes of problems. And these problems become harder to solve if you really completely separate relational from object level features. So we're advocating something like a middle of the road kind of approach. And that's what our architecture is about. Next slide. So I won't get into the details of the ESBN architecture, but just to show you, just to give you an idea of how this works, basically, as I said, in a transformer, the query, key, and value vectors are linear transformations of the object level encodings. And so what this architecture does is it separates keys and values. Essentially, there's one processing stream for values and another processing stream for keys, and they're sort of delinked from each other. What you do is you define a binding between keys and values through external memory. So you store in external memory, you store a key and a corresponding vector of values from it. But the processing for the values and the keys is done separately. So what happens in this architecture is that input objects are encoded through an encoder, and they are encoded into values, value strings. And so at any point in time, you have a bunch of values stored in memory and a bunch of keys stored in memory. And what you do is you create something like the equivalent of an attention score. It's not exactly the way the transformer works, but it's very similar. They're parallels. The output of this attention mechanism is a key and a confidence value associated with that key. And you encode the key and the confidence value into, into a key which is input to a recurrent neural network, basically an LSTM. And the output of the LSTM is a predicted key and an output, and you use the system to basically, so essentially, if I'm putting in a sequence of objects, I can train both the encoder. So there's a deep network associated with the encoder. And of course, so the two things that have to be trained here are the encoder layer and the LSTM, and these can be trained using basically training examples. Now, so one key benefit of this approach, this was published in 2022, I think, is if you see the bar graph on the right-hand side, which we're basically using only 5% of the training set of data available to this basically the training data set that was used for this example. Using only 5% of the training data set, you get 100% accuracy, which is the red bar graph on the very right. And you can see the accuracy of the other systems, including a transformer, they're very low. These are for very specific Ravens matrix type computations. So I kind of went through this very fast. I'm going to hand off to my student, Mohamed. You have about 25, 30 minutes, maybe.
Yeah, thank you so much, Professor. So the idea is to introduce a neuro vector symbolic alternative to the relational bottleneck. So the key contribution of the proposed architecture are to reduce the interference between the object level and relational information in a single hyperdimensional structure. We will introduce an efficient and novel HD attention mechanism using bipolar vectors to capture relational information. We will bind the symbolic hypervector with the object relational structure to carry positional information using Hadamard product. And with this structure, we were able to achieve 2 times better accuracy than the state-of-the-art on relational tasks. We have also a better generalization and from 2 to 7 higher computational throughput. So the tasks we will discuss are split into 2 categories depending on the reliance on object level feature. So we have purely relational and partially relational. So purely relational means that the task depend on the relation between the input object, but less on the object features themselves. While for partially relational, it depends on both, on the object level feature and the relation between the object. Now, these 2 tasks, these 2 type of tasks could be either discriminative, meaning that we will have a single element as an output, or a sequence to sequence, meaning that we will have a sequence as an output. So here we present 2 examples of one of a purely relational reasoning task and one of a partially relational reasoning task. On the left, we have a card sorting example. Here we have 4 cards, and the task is to sort these cards based on their value. So the output should be 1, and then 4, and then 3, and then 4, and then 7. Now, the output itself is the position of this card. So here, the value 1 corresponds to the position 3, then position, then the card 3 corresponds to position 4, and then 1, and then 2. On the right example, we have a custom summation of the card where the output is the summation of the card value and the previous card value. So for the first sequence output, we have we have the output is just the value of the first card. For the second one, it's the value of the second card plus the first card. So 7 plus 4 equal to 11. Then 1 plus 7 equal to 8. Then 3 plus 1 equal to 4. Now, what's the difference between purely and partially relational task? For purely relational task, if, for example, the card C3, you replace 1 by 2, the output will remain the same, meaning that the task is not fully relying on the object level feature. While for the partially relational task, if you change the value of C3, for example, the output will completely change. Now we will introduce all the datasets that we will discuss later. So dataset 1 consists of pairwise ordering, and the data is it consists of generate a set of random vectors of dimensionality k, and to associate a dominance relation to this object based on their index. For example, OI will dominate OJ if I is greater than J. So here we give an example with n is equal to 4. We have 4 random vectors, y1, y2, y3, and y4. And we associate y3 is equal to O1, y1 is equal to O2, y4 is equal to O3, and O4 is equal to y2. And the idea is to try to guess whether a pair yi and yj is classified as dominant or not, meaning that, for example, if we have y3 and y1, so so y1 will dominate y3, but here we have y3 is on the left and y1 is on the right, so we will classify this as non-dominant, meaning that y3 is not dominating y1. Okay. Do you have questions so far?
So I think, Mohamed, can you go back to the last slide?
Mm-hmm.
So I just want to say one thing here in this example. Basically, the way so you're probably thinking, how does this thing work? So what the system does is so the way it's trained is you give it 4 cards. So the system just reads 4 cards using uh, uh, just the visual images of these 4 cards. And what is also supplied with the 4 cards is the output target vector, which is 3, 4, 1, 2. So I give you 4 cards and I give you 3, 4, 1, 2. And I don't know the rule. I don't know if it's a you know, I don't know the rule that's assigned that is getting you the 3, 4, 1, 2 from knowledge of those cards. So I don't know if it is what the rule is. Is it the rule on the left, or is it the rule on the right? So I don't know the rule. And basically, if I give you certain examples of sets of 4 cards and I give you the output target, then for an arbitrary set of 4 cards, can you tell me what the output target should be? Because the system doesn't know the rule. It has to figure that out from the examples that it's fed. Mohamed, keep going.
Yeah. So the second data set is the card sorting that we were already discussing. So the first example here shows 4 cards that we need to sort. The second example shows another set of cards, and we need to sort them based on their value, but we need to output the index of each card. So here we have a discriminative partially relational task. The idea is we give a sequence of 3 cards, and we need to generate an output card. This output card should have a value equal to the sum of the 3 input cards and the shape of the first card. For example, here we have 1, 3, and 4. If we add them up, we'll get 7. So the output card should have value 7. And
8.
4 plus 3 plus 1 is 8.
Yes, yeah, sorry. It's 8. And the shape should match the shape of the first card. For the second example, we have 4 plus 2 plus 1 is equal to 7. And the shape of the output card should match the shape of the first card of the input sequence.
So just for a quick recap, basically, if we give you sequences of 3 cards and I give you an output card, but I don't tell you how that output card is obtained, right? You're trying to figure out what is the rule that's applied to get me that output card. The system does not know what that rule is. So the way it's trained is I keep giving it 3 cards. And these are images of 3 cards, and it. The output card, the last card, the first output. So basically, for 3 cards, I have an output card. I give you 3 cards and an output, and I train my system, but the system doesn't know what is the rule that is used to derive that card, and it has to figure it out.
So the fourth data set is inspired by the Raven matrices problem, and it consists of taking 2 objects and predicting whether they are similar or not. And we made this task more complex by blending the 2 gray objects into a single image and try to guess from that image whether it contains a similar object or different objects. So the idea is to take that image, to forward it to a pre-trained CNN, and from that CNN we get a sequence of features, and we need to tell from this sequence of features whether it contains identical object or different objects. So these two other tasks are also derived from the Raven matrices problem. So the dataset 5 is called SVRT, similar or different, and it consists of binary classification image, and we need to guess whether it contains a different shape or a similar shape. For example, in image A, we have a similar shape. In image B, it's different shape. The complexity of this task is from the shape of the object, which are randomly generated. So dataset 6 is similar to dataset 5, but the rule changes. Here we need to guess whether one object is inside another or is outside the other. Now we have a sequence-to-sequence partially relational task. And we have discussed already that in the previous figure where we need to do a card summation. So the idea is to have a sequence of n cards. Here we have a sequence of 4 cards, and we need to guess the output. The abstract rule is to take, so the first output should correspond to the first value. The second output should correspond to the value of the second card plus the value of the first card, and so on. So here we have 7 plus 4 is equal to 11, 1 plus 7 is equal to 8, 3 plus 1 is equal to 7. The next data set, it's also a sequence-to-sequence partially relational task, and it is based on a text, not images. And this is mathematical reasoning, and it is introduced by Google DeepMind. So the idea is to have a question, and you need to give the answer of this question. For example, here we have a comparison, which number in the list is closest to 20, and the model need to guess that the answer is 18. So the input and the output are tokens, and they are a token of characters. So here in this slide, we will introduce the mechanism of the relational bottleneck. And what's the difference between the relational bottleneck and the regular self-attention mechanism? On the left, we have the self-attention mechanism where objects are mapped to queries, keys, and values using linear mapping. And we used queries and keys to build a relational tensor composed of attention scores. And these attention scores are used to mix the values to get encoded output. The problem with this architecture is that the values are derived from the objects, meaning that the relational information here in block 2 will interfere with the object level feature derived from values. On the right, we have the relational bottleneck scheme. So we used the objects to build queries and keys, and then from them we build the relational tensor. but the values are disentangled from the object. They are derived from independent symbols. Those symbols are trainable vectors, and relational tensor is used to mix these encoded symbols to get abstract output. The issue with this approach is that it loses the object level feature as values are derived from independent symbols. And here we have our the VSA alternative. So we will benefit from the high dimensional space, allowing to mix object level feature and relational information inside one structure without interfering. So we start from a set of objects. We encode them into a high dimensional space using an HD encoder. And then we apply a sequence pooling, meaning that we will reduce the size of the input sequence by doing bundling operation. And then we will construct the HD relational tensor. And this relational tensor will be used to mix the hypervectors. In parallel, we have a set of symbols that we will map to the high dimensional space with an HD encoder. And we will apply the same sequence pooling. And finally, we will bind the encoded hypervector with the symbolic hypervector. And this will carry both object relational feature and positional feature. Is it clear so far?
If I may ask, this relational tensor, so what's inside of it?
This relational tensor is composed of attention scores that we will compute with a novel HD attention mechanism that we will introduce in the next slide.
Okay.
So in this slide, we introduce the HD attention mechanism. So the idea is to get the correlation between hypervectors. The only problem is that in high dimensional space, hypervectors tend to be orthogonal, meaning that if you compute the attention score the way it is done in transformer, this will lead to quasi similar, so it will lead to almost zero similarity. So that's why we used this bundling operation. So the idea is to compute the cosine similarity between the bipolar version of HOI and the bipolar version of HOI bundled with HOJ. And to make this computation efficient, we will benefit from the speed up of the Hamming distance. So here we provide a proof how to move from the cosine similarity in bipolar element to the Hamming distance. So as you can see here, the cosine similarity and the Hamming distance are correlated with this formula. And we just need to compute the Hamming distance using XOR operation, which is hardware friendly. And from that, we will get the cosine similarity. Here we present a high-level architecture overview of the resolve used for sequence-to-sequence task. So in red, we have the path of the object level feature. In green, we have the path of the positional information, and in blue, we have the relational information. So the input sequence is fed to an attention-based encoder composed of a sequence of self-attention transformer, which is fed to the HD encoder and mapped to high-dimensional space. Then this sequence is compressed using sequence pooling, and then is encoded using the HD attention mechanism. This encoded set of hypervectors are binded with the positional or symbolic hypervectors, and the final output is mapped back to low-dimensional space and then forwarded to attention-based decoder to get the final output. The attention-based decoder is composed of a set of self-attention mechanism and cross-attention mechanism. Here in this table, we provided all the trainable elements of the resolve and all the baseline we compared against. We have the transformer. So for the transformer, we have WQ, WK, and WV. For the relational abstractor, we have WQ, WK, WV, and the set of samples. For the ESPN, we have the encoder, we have the LLCM weights, we have the key weights, the gate weights, the confidence gain, and the confidence bias. And for the resolve, we have the HD encoder system and the set of samples. And all these components are trained through backpropagation. So here we list different type of architecture used for different tasks. For discriminative purely relational task, we have only the resolve module followed by a fully connected layer. For the sequence-to-sequence purely relational task, we have an attention-based encoder followed by the resolve module, then a fully connected layer to map back to low-dimensional space, and then an attention-based decoder. For partially relational task, we have an attention-based encoder followed by the resolve module and then a fully connected layer. And for sequence-to-sequence partially relational task, we have an attention-based encoder followed by resolve module, then a fully connected layer, and the attention-based decoder. And so the attention-based decoder will take as input the output of the fully connected layer plus the output of the attention-based encoder, because it relies more on the object level feature. So here we presented the baseline we used to assess our model. So we have, for the discriminative purely relational task, we have we compare the resolve against MLP, CoralNet, BreadyNet, the LEN, which is a neurosymbolic architecture, the abstractor, and the transformer. For the discriminative partially relational task, we compare against relational abstractor, the ESBN, the CoralNet, and the transformer. And for sequence-to-sequence purely relational task and partially relational task, we compare only against relational abstractor, as the other baselines such as CoralNet and transformer don't provide a good accuracy compared to this baseline.
So Mohammed, how much more time do you need to finish? We're sort of you need to ramp up a little bit.
Yeah, 10 minutes.
Okay, is that okay?
Should be okay. So we shall leave some room for questions.
Yeah. So
So
Mohammed,
if
try to
you,
speed up.
yeah.
Okay. So here we have the results of pairwise ordering. As you can see, the resolve outperform all the baseline model, and we used as small training samples as we can. Here we assessed the relational abstractor for card sorting, and as you can see, we have high accuracy level compared to the relational abstractor, and this is more obvious for the 8-card sorting. And one can observe that the resolve without the attention-based encoder achieve better results than the resolve with the attention-based encoder, and this is due to some overfitting problem resulting from the small training size. So here we have the result for the discriminative purely relational task. So the dataset 3, the card generation. As you can see, the resolve without the attention-based encoder outperform all the other baseline here by almost 2 times than transformer. Similar thing here for the art, similar and different, except that for this task, the baseline are close to our resolve, and this is due to the low complexity of this dataset compared to the card generation. We have the same behavior for the SVRT, similar and different, and the inside and outside pattern recognition. So for the card summation, we outperform the relational abstractor by almost 2 times. And here it's more than 2 times actually for the 10-card summation. So here we presented the result for the mathematical reasoning. And we have the token-wise accuracy and the full sequence accuracy for 4 kind of problems. So numbers is factor, comparison closest, arithmetic nearest root, and algebra 2D. And we also outperform the relational abstractor and the transformer. Now, as an ablation study, we decided to remove the attention-based encoder and try to make the samples fixed and non-learnable. We see here that the resolve without the encoder and with learnable sample achieve the best results for purely relational, partially relational, and discriminative partially relational task. And this is due to the fact that the encoder itself will add a lot of trainable parameters. And as we have a small number of samples, this will lead to overfitting. But learning the samples helped getting the positional information. So here we presented the computational overhead of the resolve without the attention-based encoder compared to the baseline. And this is assessed on an NVIDIA GPU. So here we have the latency, the parameter count, the number of operation per second, and the throughput. As you can see, we outperform all the other baseline by here, for example, it's from 2 to 7 times better than the baseline. For the parameter count, it's much smaller as a model, and for the latency, it's faster. Also, we have studied the impact of the HD dimensionality. We varied the dimension of the hypervector from 1000 to 6000, and this is for card generation task. And as you can see, the accuracy increased as we increase the dimension of the hypervector, and this is expected. The only problem is that if you increase the dimension of the hypervector, the overhead also increases. And as you can see, the model size increase by 8 to 9 times compared when moving from 600 to 100. We assessed also the resolve module against noise. And here the noise is injected inside. So the task is 10 card sorting, and we inject salt and pepper noise inside the cards. And we varied the noise level and see the noise resilience of resolve compared to the relational abstractor. And here, as you can see, the resolve is much more robust to additive noise. So as a conclusion, resolve provided a high accuracy on various purely and partially relational tasks compared to baseline. We have better generalization using fewer data sample compared to the state of the art. We have a lower memory footprint and faster inference and better noise resilience. So as prospective work, we want to discuss more complex reasoning tasks with more complex abstract rules, and also apply reasoning on multimodal datasets involving images, audio, and text. So this work was supported by this NSF grant and the School of Georgia Tech. And thank you so much. So I will be pleased to answer your question.
Thank you, Mohamed. Thank you very much. We have some time left for questions. I probably want to start with one rather technical from the chat. I also had a similar question along your presentation. So it concerns the operation of superposition or bundling. I mean, in your resolve pipeline. So when you basically, I think you call it sequence pooling.
Sequence pooling, yes.
So what are you bundling with what? So that
yes. So yeah. So for example, if we have let's say 160 sequence length, we take the first 4 element of the sequence. We take their hypervector and we bundle them together, and we move to the next 4 sequence element and we bundle their hypervector together.
So like a sliding window.
Yes, a non-overlapping sliding window, I would say.
Okay. So when you say next 4, that's numbers 5 to 8, not 2 to 5.
Sorry.
So when you say next 4, it's not like you do 1 to 4 and then you do 2 to 5 and then you do 3 to 6.
No.
1 to 4 and then 5 to 8.
Yes.
And then 9 to 12.
Otherwise, we will not reduce the sequence length.
We have a raised hand by Aileen.
Hi, thank you. Sorry, I was wondering if you could, this is also another technical question. I was wondering if you could back it up to the slide diagramming how the model works.
Okay.
Just if I could get a little bit more light shed on it. So, I'm not entirely clear on what the high dimensional encoder is doing.
Yes.
So your objects and your symbols are just
So the high dimensional
okay.
encoding is a 1D convolutional layer with a kernel equal to either 1 or 3, depending on the task, and the number of filters is equal to the size of the upper vector.
Okay. Okay.
Mm-hmm.
1 or 3. How did you stumble upon that?
Sorry.
Never mind. Silly question.
No, I think some details can be probably understood from the paper itself, but
yeah,
it's a valid question. I also had a question about details of encoder, especially after Mohamed's comment that the vectors would be quasi-orthogonal after it. So that's kind of interesting. Sorry, I interrupted you.
No, it's fine. No, the quasi-orthogonality makes sense, at least from like the start of training, because if we're expecting the kernels to be randomized at the start, then that would be an expected result. Do the vectors become more similar over the course of training?
The vectors, they might be similar as you go over the training, but if you apply this sign here, they become orthogonal.
I see.
So let's see if we have Sven.
Yes. So thanks for a nice talk. Similar vein into more details into the model. If you could go to the slide 22, I think.
Okay.
I was wondering about I understand you correctly that the symbols are not input dependent. They are just your sequence that give you your position encoding, basically, right?
Yes. Yeah.
And so can I think of this as essentially a position encoding like rope or anything else that you would do, just that it's trained and applied later in the architecture?
Yes.
So, okay. And how much do you gain from the training and how much do you gain from the fact that it's applied later? So if you would just apply like a cosine version of this rope, for example, as your symbol encoding and apply that at a later point.
Yeah. Here in the ablation study, I put the fact that the symbols are learnable, trainable, or just randomly generated.
Okay.
So with the encoder, if they are randomly generated, they provide better result. And this is expected actually. This is due to the fact that you increase the number of trainable parameters while you have a not short, but small training data set. And this will lead to overfitting.
But you could make them neither trained nor random. You could make them a sequential system, basically, like you have your one time stack vector that you bind over and over again to make your position encoding already have the information of one time step after another, right? So you can make a unit time step vector and bind that over and over again, and therefore already introduce the information of a sequence, for example, and not have just random vectors in a I'm not sure if I'm making sense right now, but maybe this is just a random idea. But this would, in my mind, give you the additional information of the sequence in here that you don't have to train for. You know that it's a sequence.
Yes, yeah. Now there is also one more thing that for before doing the attention encoder, we apply positional embedding as well.
Ah, okay. So there is a positional encoding already in the.
Yes.
Okay. And then you provide basically the position encoding a second time.
Exactly.
Through the symbol.
With the high dimensional symbols. Yes.
Okay.
So there's one symbol per object.
Yes.
So the number of symbols is the same as the number of objects. So for example, if you're training with 10 cards, then there are 10 symbols, basically.
So does that mean you have to know the number of objects before the task?
Yes.
In a language case, that would be your vocabulary then?
That's right.
Okay. Makes sense.
Yeah, except the only thing here is that the symbols themselves are trainable.
I have a high level question. Of course, I'm kind of excited to read more in the paper. But can you deduce the rules by the end of learning? I mean, can you interpret your learning? I mean, what was the rules?
Yes, I think this is the next one of our next step is to have a separate model that will try to interpret the actual rule by outputting a sentence, for example.
Mm-hmm.
So Evgeny, one thing that's happening here is that basically the input to the system are basically 24 by 24 or pixel images of these cards. So the input to the system is actually pixelized versions of each of those cards.
Mm-hmm.
And so we're giving you, let's say, pictures of 4 cards and then picture of 1 card. The system doesn't know what the rule is. And I could make those rules very complex, as you can see.
Yeah, absolutely.
I mean, we're so right now we've used benchmark data sets from prior research. So all of these things are prior published data sets. And we're comparing based on those data sets. But I can imagine one could really crank up the lever, make it really hard. You can have very complex, for example, the rules could be nested in nature.
Yeah.
If this happens, then do this, else. It could be a whole bunch of if then else statements. And then the system has to figure out exactly what that rule is. Now, as you keep doing this, then I think we'll have to see how to, what modifications we need to make to our architecture to make it work. But so far we're doing better than anything that's out there. And hyperdimensional computing, the working in the HD space is giving us significant computational benefits.
Tony, you unmuted yourself.
Yeah, really interesting stuff. I was wondering, have you tried applying this to the ARC problems, the abstraction and reasoning challenge?
I didn't try, but I came across of this challenge. Yeah, maybe this is the next step.
Yeah. Okay. Yeah, and another question. So very early on in the first talk, you were talking about the different types of information: object level, relational, and positional. Just a question there. Is there really a what's the difference between relational and positional, or could you just view one a form as a type of the other.
Yeah. So relational information is just the correlation. You can think about just the correlation between objects. Okay. For positional, it's depending on the position of that object.
Right, but why isn't that just another type of relation?
Yeah, so basically think of so there are two concepts here, right? One is that of position, and the other is one of you can think of this as magnitude, right? So if I define a relative order, an apple is bigger than an orange, right? So so I need to capture this notion that or an apple is more tastier than an orange, and one could argue with that depending on who you talk to. But let's say we define a notion of bigger in terms of taste and say apple is bigger than orange, right? But then position information is also important. I mean, does the apple come first? Does the orange come first? I don't know if this makes sense.
Yeah. It sounds like you're saying that that positional is richer than relational. Would that be a fair characterization?
No, I would argue it depends on what you're trying to do. So basically, there are object level features, and there are relations between objects, right? So the relations between objects can be defined depending on what, it's a role-based system. So it depends on how you define that role. So how is A related to B? I am, this person is my nephew or this person is my uncle, right? So that defines a level of seniority. But does the uncle come first in a queue, or how's this thing presented? So that's the position part of it. I don't know if this is making sense.
Yeah. That makes some sense. Yeah, part of the reason for my asking is that I've been thinking about this, wondering if we have a something that can do a good job with like positional bindings. Can that then basically do everything that you need to do for relational?
Yeah, so in this case, if you saw the architecture, the encoder is using a traditional transformer-based architecture, so it's got positional encoding built into it. At the symbolic reasoning, the symbols are sort of abstracting out some structure from this from the data.
Yeah. Okay. Thanks.
We have another question from Eileen.
Oh, sorry. This is like minor, like final clarification. So by relational information, you really just mean like an ordered, like co-occurrence sort of relationship, whereas positional information is like an absolute position within a sequence.
That's right. Yes.
Yeah. Okay. Thank you.
So does A supersede B? That's a relational information. So and that can be abstract, or is A greater than B? That's relational information.
So let's check if we have kind of last question, because we can take other questions offline by email. Any more questions? Well, if not, then it remains to thank our speakers again. So it was really exciting talk, and I personally look forward to reading your papers in detail and monitoring the progress. So thank you very much for presenting your work.
No, thanks for inviting us. I thought this would be a good opportunity for Mohamed to speak.
Absolutely. And I think, as I mentioned, so it was quite some time ago we had a talk on reasoning. So that's a very hot and interesting topic. So, thank you all for joining us today, and stay tuned. So next time, VSAONLINE will be active again in 2 weeks from now. So check the program on the website. So thank you all for coming.
Thank you.